Welcome to part 3 of podcast lecture on photonics. This emphasizes semiconductor nanoparticles and quantum dots. This shows the outline. I will start by giving an overview of semiconductor nanoparticles in a historical perspective. After mentioning several applications, I will remind about optical properties of semiconductor materials and emphasize the alterations experienced by reducing size of semiconductor. I will then revisit the quantum dot laser. Some history of semiconductor quantum dots and nanoparticles. It will be biased. I've worked with this a long time, so it's flavored by how I remember it. One can trace studies of charge capture by nanoparticles back to the 1950s. And I remember we were talking about the possibility of making memory devices with quantum dots in the 1970s. In the 70s, quantum well lasers were demonstrated, and it was rationalized the advantages of making a quantum dot laser. During the 80s and 90s, there were many groups working on quantum dots, motivated by making a quantum dot laser. So there was an attractive application that motivated. It was also many interesting issues in the theory and challenging experiments and technology inventions. There were many spin-offs that might not have been anticipated at the start. For example, commercial quantum dots for biological labeling were on the market long before quantum dot lasers. Other spin-offs that can be mentioned are light-emitting diodes, quantum dot flash memories, quantum dot TV screens, quantum dot down conversion in solar cell. One thing I've learned from the history is that some application may take a long time to develop. But even so, much other useful and interesting stuff can come out of it. Quantum dot lasers are now on the market. Here I show some early applications of nanocrystals and quantum dots in devices. Here is shown quantum dot memory, light-emitting device of 1.5 micron IR radiation, solar cell down conversion, and a UV photodiode. Let's show the quantum dot memory, even if not a photonic device. It's an improvement over regular flash memory, where you have an MOS transistor with a floating gate. There is a tunnel oxide and a control oxide. You control the device by opening or closing a channel between the source and drain. This is controlled by charge on the floating gate. The charge you get by enabling electrons to tunnel to or from by putting a high voltage on the control gate. The trend for flash memories followed the general trend of increasing package density and scaling down device dimensions. That made it vulnerable to defect creation in the oxide, which could short circuit to the floating gate, and then the device would be destroyed. But if one divides the floating gate up into many nanoparticles instead, then the device may work, even if one nanoparticle is shorted. Here you see an example of a commercial nanocrystal flash memory. The flash memory is integrated on a microprocessor chip. Then here is the solar cell I showed earlier. Here we have a dielectric functioning as an anti-reflective coating, AR, on top of a standard silicon photovoltaic solar cell. There are also quantum dots in the anti-reflective coating layer. The dot will absorb UV light and emit photons with energy close to the silicon band gap. People have studied down conversion in quantum dots. You have a UV high energy photon coming in. This can be split up to 2 photons or more in the quantum dot. Thus you have 1 photon coming in and 2 going out, which can create 2 electron hole pair in the regular solar cell, say silicon solar cell. The UV photon would only create 1 electron hole pair in silicon, and the rest would be lost as heat. The extra energy meaning the excess of bandgap energy. The other thing is that the absorption in the silicon solar cell is highest for UV, so the photon is absorbed close to the surface. There you may have recombination centers, and then that photon is not contributing to any current in the external circuit. So the situation was one UV photon in and generation of two or more electron hole pairs, recombining as excitons and giving out two or more photons. Say we have a photon of 3 electron volts coming in, and we get two photons of 1.1 electron volt each going out. Why and how is that done? Why does it happen with a quantum dot semiconductor, but not with a bulk semiconductor? Well, hang in there and I will tell it later. There are also many that worked on down conversion or quantum cutting in the anti-reflective layer by rare earth atoms, which may provide suitable energy levels in the F-shell. These are not so much influenced by the matrix. They may communicate with the semiconductor nanoparticle, which may provide the absorption of a UV photon. The excitation energy may be transferred to one or more rare earth atoms. In the sketched schemes to ytterbium, the ytterbium ion will emit one or two photons with an energy slightly higher than the band gap of silicon. Let me tell us some device developments that have been going on using silicon nanocrystals, which we were involved in 10 years ago. This motivation was within optical amplifiers. The goal was to replace the optical amplifier in the bottom left figure with that in the bottom right figure. The bottom right uses silicon nanocrystals and could be produced very cheap, while the bottom left is expensive because it contains a temperature-stabilized high-quality laser. This is within optical communication occurring at 1.5 micrometer used in today's fiber, because the optical absorption has a minimum there in the optical fiber. This 1.5 micrometer coincides with emission from erbium. So the traditional optical amplifier uses a piece of erbium-doped fiber. One is then creating population inversion in erbium by pumping with a laser, which has to match exactly the level of erbium. In the cheaper device in the bottom right, erbium is excited by using silicon nanocrystals as collectors, and they can be excited with white light, which is much cheaper, and transfer the excitation energy to the erbium ions. Here you see light emission device made in MOS technology with quantum dots coupled to rare earth ions for specific wavelength emissions. One can scan light sources electrically. It is made for mass-produced disposable quick diagnostic medical tests, while the traditional way is to use a tunable laser mechanically stepped over the surface. Nanocrystals and quantum dots are also used in solid-state lighting. Here the quantum light-produced platform is shown. There are many others. They are energy efficient and can have superior color. It is stated that 1/5 of all the energy generated worldwide is used for lighting, so efficiency is important. These devices also switch on and off very fast, and it has been suggested and tested to use these as combined lighting and distributors of local network by switching on and off very fast. The eye will not notice this, and it is faster and has larger bandwidth than present Wi-Fi networks. It's called the Li-Fi, often. Forget 3D, here comes QD TV. Well, the QD screens constitute the largest use of quantum dots today. They are used in TVs and in phones, One exploits that one can control the color of quantum dots by its size. Here is how the quantum dots are mostly used for the screen. In present-day mass-produced screens, one is optically exciting the quantum dot. By a backlit layer, typically blue, is used. Then there is a layer of quantum dots. These can be put on by jet ink printing. And then it has a liquid crystal layer on top. Here we see another exploitation of the fact that quantum dots can show different colors dependent upon their size. They are used for labeling different parts of biological tissue. They are introduced into the tissue dissolved in a liquid. The quantum dot is functionalized to a biomolecule on its surface to attach to a specific molecule in that tissue. Here is shown laminin in a mouse kidney labeled with green quantum dots. Blue and red quantum dots are attached to other parts. These quantum dots shown here were of the so-called core shell type. They typically have a semiconductor material in the core that determine the color that is adjusted by their size. What is the purpose of the shell? It is to passivate the surface, and it is illustrated to the right. One wants the electron hole pair to recombine within the core. There will be surface states on the surface that might give non-radiative recombination and not emission of the right color. The shell makes most of their wave functions stay in the core. The shell is often a material with the same crystal structure as the core. The shell atoms are ideally repeating the periodicity of the core, leaving few localized states at their interface. Another application of quantum dots in biomedicine is for photodynamic therapy, PDT. Here one functionalized the quantum dot to attach to a tumor cell. It is also functionalized to make singlet oxygen and radicals that are toxic to the tumor cell. The reaction is triggered by visible light generated by an upconversion process in the quantum dot in response to near-infrared light. One uses quantum dots to make entangled photons intended for use in future quantum computing. You have heard about quantum entanglement in Chapter 3. Einstein referred to it as spookiness at a distance. Entanglement can be achieved in the decay of a Exciton. So that is a quasi-particle made of two other quasi-particles, excitons. And the exciton is made up of two other quasi-particles, electrons in the crystal and holes. Entanglement of bi-excitons requires two decay paths with different polarizations, but otherwise indistinguishable. This can be achieved under certain circumstances. You are not required to understand or learn that. This is the case if delta x in the figure goes away for symmetry reasons, and the intermediate state of the exciton is degenerate. The quantum dots here are made of indium arsenide having a small band gap grown on top of pyramids of gallium arsenide having higher band gap. Let's look again at the most important details that are different for a bulk semiconductor and quantum dots. The most important may be their electronic structure. The bulk semiconductor has a band gap separating a valence band that is occupied and a conduction band that is unoccupied. And it is transitions between occupied and unoccupied states that are involved in the optical response of the material, both for absorption and for emission. For nanoparticles, the electrons will be confined. For a quantum dot, we have discrete energy levels, not bands, due to the confinement. We can think of it as 3D particle in box to qualitatively understand, for example, the important trend that the band gap increases with diminishing size. We get a blue shift in luminescence emission with decreasing size. For small clusters of atoms, you get the same tendency by thinking of what happens with atomic orbitals when you chain more atoms together. The levels split up and fan out. So again, color emitted by quantum dots can be between individual levels. These levels are more separated for smaller particles. You can understand that trend from the familiar particle in a box problem. So for these solutions shown here of quantum dots showing photoluminescence, the larger ones are red and the smaller ones are blue. That you will additionally have lowering of energy by excitons, and exciton states for that matter, are not included here. For typical semiconductors, the exciton binding energy is small compared to the kinetic energy for strong confinement. But in what we call weak confinement, the blue shift is given by confinement of the exciton. In strong confinement, the blue shift is due to confinement of electrons and holes separately. The electrostatic interaction between electron and holes are larger than under weak confinement, but the exciton states are not populated. The wave functions of electrons and holes are no longer correlated in strong confinement. I'll show a comparison between the luminescence intensity from bulk silicon and quantum dot silicon. They can be excited optically or electrically. It is in very weak, no noticeable emission from bulk silicon. It's black. Whereas we get bright emission from quantum dot silicon, shining white. The question is, why is it like that? First off, there is very weak emission from bulk silicon because it is an indirect semiconductor. Of course, if you excite so heavily that it will get hot and glow, it will emit. But long before that, quantum dots will win the intensity race. In an indirect semiconductor, you will need the help of a phonon to go from the bottom of the conduction band down to the top of the valence band, where the likelihood to find a hole is largest. The need for that is in order to conserve momentum in the recombination process. What is different in the quantum dot is that the momentum is not a good quantum number. Due to the Heisenberg uncertainty principle, the possible k values are extended compared to bulk. The position in the quantum dot is relatively well defined. Then its momentum cannot be that well defined from Heisenberg. That's tried illustrated by the state is extended in a large region of K around the minima and maxima, and you can have conservation over a large region in the bottom figure. Semiconductor quantum dots may by itself be a favored place for having one photon in and two or more coming out, as we talked about. This is called quantum cutting. It is by creation of multiple electron-hole pairs, sometimes called multiple exciton generation, unfortunately. You may ask, Siri,
why not collect the electron-hole pairs directly, instead of creating photons that has to be collected by the solar cell?
Good question. It's just not so easy to do that efficiently from the quantum dot. But in X-ray detectors made of bulk semiconductors, you rely on multiple electron-hole pairs being collected. For photons in the visible range, only one electron-hole pair is generated per photon. However, in quantum dots, you can have more. Because, first, due to confinement, the electron and hole in the quantum dot are interacting more than in bulk, where they can be separated. Second, the excited carriers may lose energy to photons, and this may happen slower in a quantum dot, where you have larger separation between levels and also quantized photon energies, so lower probability for a match. And finally, the creation of an electron-hole pair from an excited electron can be considered as an O-shaped process involving three energy levels. The requirement of matching states that is possible is relaxed by the Heisenberg uncertainty principle of the confinement. Thus, more electron-hole pairs are created in a quantum dot than in bulk. We will do some simplified calculations together. As I said, quantum dot lasers have taken a long time to develop into a commercial product. There are several companies on the market. I will explain why they have the advantage of good temperature stability and low threshold compared to quantum well lasers, for instance. This shows schematically the distribution of elements in an embedded quantum dot. Quantum dot can be a semiconductor of small band gap, while the matrix surrounding it can have a larger band gap. Here are some examples. For you communications, it would be indium arsenide quantum dot with a small band gap, in gallium arsenide with a larger. I will, for the example, consider a gallium arsenide quantum dot in an AlGaAs matrix and ask, how big is the quantum dot for the purpose of making a laser? To answer that, we need to take a look at the band diagram of the active part of the band diagram of the laser. What we see is a cross-section through one of the quantum dots of gallium arsenide seen as green. The turquoise are then AlGaAs with a higher band gap. There is an energy offset delta EC in the conduction band of these materials. There is also an offset in the valence band. So electrons inside the quantum dot are confined by the potential of the conduction band, while holes in the quantum dot are confined by the potential of the valence band edges. We get discrete levels E1 and E2 in the quantum dot. We ask, how small can the quantum dot be? If the quantum dot gets smaller, the distance between the levels gets larger, and if the energy level E1 gets larger than the offset delta EC, the electron level will not be confined. So E1 need to be smaller than 0.03 electron volt. Now we can use the particle in a box expression for the energy level. It contains the diameter of the quantum dot, and we can calculate that the diameter must be larger than 4 nanometer. Then we may ask, how big can the quantum dot be? If you want, you can stop there and think yourself. Well, we want to use this as a laser, and we want to have lasing between discrete levels. Therefore, we want only one of the levels, E1 and E2, to be occupied. So their distance between them has to be larger than a certain lower limit. What would that lower limit be? Again, you may stop and think. I say we have to make the difference larger than kT. Then again, we use the particle in a box expressions. We get that the quantum dot should be less than 12 nanometers. Then let's just look at simplified how the quantum dot laser may work. We pump it electrically, so we inject electrons and holes into the semiconductor. Electrons will fall down into the quantum dot and holes will float up into the quantum dot. Thus we get many electrons there and holes, so we may have a population inversion. We get photon emissions from electrons recombining with holes. They have a relatively well-defined wavelength. As these are reflected from the edges of the piece, we get stimulated emission. Let's see why this quantum dot laser is more favorable than a quantum well laser. Then we compare the density of states for those situations. For quantum dots, we see these sharp lines in the dots to the right. For the quantum well, we see this stepwise function. So there are many more levels involved in the quantum well laser, not only those we finally want. This makes a quantum well laser in principle hotter than a quantum dot laser. So the quantum dot laser may not need cooling. Let me finally just mention random lasers. This can occur in thin films of nanocrystals. One gets one or more random total path lengths that form a cavity for the light. Here we have an example of zinc oxide nanocrystals embedded in silicates, yielding 6 orders of magnitude increase in the band edge luminescence of zinc oxide. The power law increase of band edge emission intensity with excitation power is consistent with random lasing theory, and there is a very low threshold of 40 microwatts, even if it's still tentative. That finishes part 3 of Nanophotonics on semiconductor nanoparticles and quantum dots. This is the original lecture outline. The next podcast on nanophotonics will cover near-field light, optical tweezers, and photonic crystals.